try a different dongle, or did you try a different dongle and now it's working?
This is actually Noah's.
Yes.
Okay. And this one seems to be behaving better?
Maybe. I'm
Okay.
not sure.
I'll be nearby just in case.
Okay.
Hello, everybody. Welcome to today's APS Colloquium. As you can see, we're having a little bit of a problem with the screen disappearing and reappearing. There's something, but JR will fix it. Anyway, thank you, everyone, for coming. And it's a real pleasure to introduce as our speaker today, Noa Zilberman. She is currently would you call yourself a postdoc?
Sure.
Still?
Yeah, of course.
But you had some fancy name now, research fellow.
I'm a postdoc.
Yeah, okay. She joined Princeton in the gravity group in physics in last year, in 2024, fall of 2024. I have been watching her work for years. As you may know, my graduate student, Tyler McMacken and Noah have been doing kind of similar stuff. And we've watched her beat us. And sometimes, anyway, I've really looked forward to having you here. And what else can I say? You got your PhD in Israel at Technikon in the group of Amos Ori. And you're going to tell us today some cool stuff about black holes.
Yes.
Noah.
Thank you for the nice introduction, and it's really nice to be here and to meet some of you before the talk. That was really nice. Okay, without further ado, I'm going to talk. So my title is No Fireworks. You will understand why. And it will be on the origin of black hole radiation. It's based on a paper with Amos Ori. Oh, okay. So basic outline. So first I will say, I do not assume any GR knowledge, so don't worry. I will try to make it as approachable as possible, but I will be happy for questions. So as an outline, the first part, which is actually, I guess, the major part of the talk, will be an introduction, setting the stage. So I will try to tell you about the Hawking effect in a nutshell, and hopefully you will know everything you need to know about it. And then the second part is about our research, and it is titled No Fireworks. Oh, okay. Okay. Yes. And it's on again. It's a bit unstable. Yeah. Okay. Yeah. Okay. So how many of you took a GR course? Okay. I can start on the board. No, seriously. Yeah. Okay. So while this is in progress, it seems like it's about to work. Perfect. Thank you. Okay, thank you. That's good for now. Okay, good. Thank you. So first part, introduction to the Hawking effect, which will be an introduction to a bunch of things. So we start with general relativity. In a nutshell, to summarize GR, I would put this equation, which has the geometry of space-time on the left-hand side and matter and energy on the right-hand side, encompassed in the stress-energy tensor. So this is the only equation I need you to know from GR, and it shows that space-time tells matter how to move, and matter in turn tells space-time how to curve. So there is an interdependence of these two things. So this is GR in a nutshell. And it has brought us many great results over the years and many predictions which turned out to be remarkable, like gravitational waves, black holes, and some other stuff. But it is not the full picture, because we know that the particles that obey these Einstein equations that I show also have quantum properties. So they have mass, they bend space-time, but on the other hand, they also obey the uncertainty principle and other quantum effects. So for example, if the particle's location is uncertain, what does it mean for the gravitational field? And there are all kinds of questions like that classical, when I say classical, I mean non-quantum, GR doesn't know how to answer. So a theory of quantum gravity is required, but we still don't have one. But even if we lack this holy grail of the theory of quantum gravity, we can still make some progress by embracing the semi-classical formulation of GR. So in this semi-classical formulation, we take, okay, so this is the equation I showed you before. We don't know how to quantize the geometry. Okay, I will show you with this. We don't know how to quantize the geometry, but we do know how to quantize the matter and the energy. This is quantum field theory. So the idea is to replace the right-hand side by its quantum version, which is the renormalized stress-energy tensor in some quantum state. And we're looking at quantum fields that propagate on a classical curved space-time. That's why it's semi-classical. Okay, now this is an interesting equation. So we have the space-time curvature. So this is the metric. This is the geometry of space-time. It induces non-trivial stress energy in the quantum fields, even in vacuum states that are maybe thought to be empty, but they're not. And these non-trivial stress energy on the right-hand side back react on the metric. So there is this interdependence. So first you can compute the stress energy tensor induced by the geometry, and then it deforms the metric. And that's how you can treat this equation. Now, these effects are very, very small. So the local semi-classical effect is typically of the order of h bar, which is the quantum. It's a quantum effect, so it's h bar. And 1 over m squared is some curvature scale of the space-time, where m is the mass of the black hole. So this is a very, very small number. This is the small number that, that governs this semi-classical approximation. So it's extremely weak as a local effect. For example, for astrophysical black holes, if you plug in the numbers, you get something like 10 to the minus 77. That's very, 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 very small. Yeah, I might have missed a very. Okay. But why is it interesting? Why are we talking about semi-classical effects? Because they can accumulate over extremely long timescales. So it's very small when it's local, but if you accumulate it, it can lead to a significant global impact. And one famous example of such a dramatic semi-classical effect is a Hawking effect. You might have heard about it. We are going to dive deep into it today. So according to the Hawking effect, there are some back reaction effects according to these quantum fields that accumulate along an event horizon of a black hole and lead to a drastic reduction in its area, and the black hole eventually evaporates. So this contradicts the classical expectations that black holes can only grow. So this is the Hawking effect. He used the semi-classical formulation I introduced to you before. So this shows that quantum effects, despite in everyday problems they can be negligible, but when considering them on black hole spacetimes, they can actually change the classical spacetime picture. So I'm going to tell you more about the Hawking effect, but let's do a short detour to read the map of spacetime that we're going to use. This is called a Penrose diagram. So let's learn how to read spacetime diagrams. So problem, our spacetime, so this is just flat Minkowski spacetime. This is space and this is time. So flat spacetime is called Minkowski. I'm going to use this word. So we have infinity at infinity. Okay, but we want to draw a map where we can put infinity at a finite location on a piece of paper. So well, Escher did some similar things. Do you know off the top of your head of some function that takes the infinite line into the infinite real line into a finite segment? Just one function that does that is the arctangents function, for example, right? So this is something you can do. You can take infinity and put it in a finite segment. Now, what do we want to do? So it's not enough to just take infinity to a finite location. What we want to do is preserve causality. So causality is this thing that determines the structure of space-time. And it is determined by light rays. So what you see here at the bottom here is the future light cone and past light cone of an observer sitting here. This is everything that can affect me, and this is everything I can affect. So causality is one of the determining features of the structure of space-time. So we want to, so we have a future light cone and a past light cone, and we want to preserve these in our transformation. So a Penrose diagram is a two-dimensional diagram which preserves causality. So now infinity is at a finite location in the diagram, and it preserves causality in the sense that light rays, which determine causality, still propagate at 45-degree angles. And at every point here, there's a sphere, so the angular dimensions are suppressed. It's a two-dimensional diagram. But the causality preserving feature is the crucial feature, and that's why, and I hope I will, by the end of this talk, you will be convinced that Penrose diagrams are really useful, because it really tells us everything we need to know about the causality and about the structure. So, okay, so this is a Penrose diagram. Now let's look at a few examples. Again, this is a Minkowski space-time. Each one of these segments is spatial infinity. Okay, so this is one light ray. It can go from there to there. This is another light ray. It can go from here to here. So we call these past light-like infinity. Past because it's in the past of the light rays, and this one as well. Light-like because it's for light rays. And then there's also future light-like infinity. So this is what you need to know about this diagram. And also, let's look at an observer, which is not a light ray. It has a future light cone, and it has a past light cone, which is everything that is in its past, and this is everything that in its future. And it can only move within its light cone. So it can do this kind of motion on the Penrose diagram, like this one, for example. So this is the infinite past for massive observers, and this is the infinite future. So this is called past time-like infinity and future time-like infinity. I'm not going to keep these just to avoid clutter, but so you know, all the observers that just sit in one place, they reach this point at the end. Okay, so this is the Minkowski space-time. Not so interesting, flat space-time, nothing happens there. So let's add a black hole. Once you add a black hole, you have an event horizon here. We will talk a bit more about it later. So now you don't have infinity here. And let's look at light rays again. So now light rays can start at past light-like infinity and reach the singularity inside the black hole. Or they can start here at the past horizon and reach future light-like infinity. Or they can start inside the black hole and reach the singularity. So this really determines the structure of space-time. And you can see that the event horizon has a special causal role. So let's look at our observer, and let's throw it into the black hole. So it approaches the event horizon. As it approaches the event horizon, less and less of its future is in our universe, and more of its future is inside the black hole. So at this point, we can still escape through this sliver, but if we are very, very fast. But once we reach the event horizon, our entire future light cone lies inside the black hole. So that's the causal role of the event horizon. The event horizon is special because of this causal role. And that's what defines a black hole. Now, everything is smooth at the event horizon. When you cross the event horizon, you don't feel that anything special happened. And Andrew here actually has a nice paper on this analogy. the waterfall analogy. So it's an analogy I like because what is the event horizon? So if you were on a ship or on a boat approaching a waterfall, at some point you won't be able to go back. So you have a motor to your boat, and at some point your motor won't be able to take you back, but you don't know exactly at which point it is. It happens somewhere far from the waterfall. Nothing special happens there. But once you cross this point, defined by that the velocity in which the river flows there is just like the velocity that you can counteract. Once you pass that point, and you don't even notice anything usual, you are doomed to reach the waterfall and to fall to the singularity. So that's a nice analogy for the event horizon. And once you cross the event horizon, you are entirely in the black hole, and the singularity is in your definite future, so your fate is going to be over there. Yes. Okay. So beyond the singularity, it's presumed to be the end of space-time, but what about this region? So here we have R equals Rs. Rs is the Schwarzschild radius that in gravitational units equals twice the mass of the body. So what happens over there? Turns out that we can extend space-time. And then we have a white hole region, other universe. So I won't talk about these, but this is the full maximally extended Schwarzschild space-time as a vacuum solution. But in fact, we know that black holes are not, they actually form in gravitational collapse. And once you add a collapsing star, all this white hole stuff it leaves the space-time. So you only have the star, and you have what happens outside the star. Inside the star, it's not the same solution. So the Schwarzschild geometry applies everywhere outside a spherical body, not just a black hole. So to show you this, I put here space-time on the right-hand side and space on the left-hand side. So now we're going to look at time slices. So this is a time slice, and we have the collapsing star. Okay, remember that each point here is a sphere. And now we're going to collapse our star, and the time slices progress. And at some point, we reach the event horizon. So now the radius of the star reached the event horizon. And at this point, the black hole is born, and you keep going, and you reach the singularity, and so on. So, but throughout this video that I showed, you have Schwarzschild outside, the Schwarzschild solution describing a black hole. Okay. Now, back to the Hawking effect, which is really a striking semi-classical effect. So I hope you now understand kind of how to read Penrose diagrams. So again, we have, this is again the Schwarzschild solution for an eternal black hole. But in gravitational collapse, this region is not applicable, as I showed you. These are pictures, by the way, from the original Hawking paper in which you introduced this effect. OK, and this is the collapsing body, and this is the Schwarzschild space-time outside the collapsing body. And this is the event horizon. So the 1 minute picture of Hawking radiation. And then I'm going to give you some points, and then we're going to go through these points. So the first one, a massive star collapses. Far away, everything looks flat. But near the forming horizon, outgoing light is extremely redshifted. I will show you more about this in the next slide. The next point is that quantum vacuum is not unique. So it depends on how you split your field into positive and negative frequency modes. We'll talk more about that as well. Then the collapse maps early modes coming from here to late modes with an exponential delay because of the extreme redshift at the event horizon. And finally, this distortion in the vacuum yields a steady particle flux at infinity called Hawking radiation. So this is the 1 minute picture. Let's go over all these different steps. So a massive star collapses. Far away, everything is flat. That's very clear, right? Far away, things decay to flat space-time. What happens near the forming horizon? So it's the red line up there. So to explain why it is extremely redshifted, let's look at two people, twins. Let's say they're twins, Alice and Bob. Alice happened to live to live forever. Remember, future time like infinity is where she's going to reach. It's in the future. It's in the infinite future. On the other hand, Bob is going to jump into the black hole. So, sorry, Bob. So he's going to cross the event horizon in finite proper time. So Alice reaches this point at infinite time, and Bob reaches this point at finite time. What does that say? So now Bob is going to send Alice periodic signals according to his proper time. So as we said, Bob is just in a boat on that river. He doesn't notice anything special happening, and he sends these signals back to Alice, who is far away. This is the last signal, and as the signals are being sent, Alice is going to receive them at later and later times, because for her, this is infinity, right? This is the infinite future. So she's going to receive the signals farther apart, until the last signal, she's going to receive it marginally at infinity. So this is actually redshift. This is the redshift. So the light that Bob sends Alice is redshifted. And this is, can be seen in the following nice relation that we are going to use throughout the talk. So what we have here is two different coordinates that track time for us. This is the Kruskal coordinate, capital U, and it behaves like the local time near the horizon crossing. So this is Bob's proper time. On the other hand, we have small u, which is called an Eddington coordinate. It is the retarded time measured by a faraway detector. This is what Alice's telescope uses. And the relation between Bob's proper time and Alice's proper time is this exponent. So this relation tells us that there is an extreme exponential redshift. Okay, this relation is going to be useful throughout the talk, so I will show it throughout. Okay, and this relation comes from the geometry and from the fact, just like I showed you on the Penrose diagram how it arises. It comes from the special role of the event horizon. Okay, nice. Let's go to the next part. So now we understand why the event horizon is a surface of exponential redshift. The next point is that the quantum vacuum is not unique. What does that mean? Okay, we are going to do quantum fields in 101. 101, but this is really a very, very crude crash course into quantum fields. So we start classically. Classically, we have a field. This is a scalar field. It obeys some equation. The geometry enters through this D'Alembertian. So this includes the geometry, and it includes the metric. So this is a classical field. Now, in order to treat it as a quantum field, we're going to promote it to a quantum operator in the following way. So it is written as a sum over modes and annihilation and creation operators. So we can decompose the field into modes that satisfy this equation, and then rewrite the quantum field as a superposition of annihilation and creation operators, which annihilate and create particles according to these positive and negative frequency modes. So the vacuum is taken with respect to these positive frequency modes. What does that mean? That the vacuum is defined, so this is the vacuum, that it's a state. The vacuum is defined as the state that is annihilated by all these annihilation operators for all modes. This is the definition of the vacuum. So again, I would like to stress that the definition of a vacuum arises from splitting the field into positive and negative frequency modes. Now, we can also decompose our field with respect to a different set of modes. It's a different basis, taking a different basis to the space. And it has different positive and negative frequencies and different annihilation and creation operators. And now the vacuum according to this decomposition looks like that. It obeys this equation. And the key is that the fact that the phi vacuum is annihilated by these operators does not imply that these annihilation operators of the other vacuum also annihilate it. This is not necessarily true given this. In other words, the vacuum in one state can contain particles in another state, because if this is not at 0, then this is not the vacuum in this state. That's the general idea. And when does this occur? When does this not imply this? When does one vacuum contain particles in another state? Well, with these modes, this is just usual linear algebra. You have two different bases, and you can relate them with transformations, translating one basis to another. These are called Bogoliubov transformations. And when positive frequencies are mapped to positive frequencies and negative are mapped to negative, the vacuum is agreed on. But when positive frequency modes in one basis decompose into a mix of positive and negative frequency modes in the other, that's when you're going to get that this is not 0, and there are some particles in the other state. So mixing positive and negative frequencies results in the vacuum containing particles in the other state. In flat spacetime, this doesn't happen because it's very clear what we mean by positive frequency, because it's very clear what we mean by time. But in flat spacetime, it's less clear. And you can actually get this, and this is the Hawking effect. So let's talk about two different vacuum states on this spacetime of the collapsing body. You have two regions and two different vacuum states. You have the in region, which is pre-collapse. The in region is here, and the modes there look like ordinary positive frequency plane waves coming from past infinity, which is just flat. And similarly, you have the out region, post-collapse, over here, in which modes look like positive frequency waves measured by a late time distant observer. Now, the vacuum ambiguity is that if the in modes and the out modes are related by this Bogoliubov transformation that mixes positive and negative frequencies, then the in modes will contain out particles. So I hope that was pretty much okay. Are there any questions on that point? Okay, so let's keep going. I'm keeping an eye on the time because we're still in the introduction, but that's okay. Okay, so the next point is that the collapse maps early modes to late modes with an exponential delay. So we're going to see it by tracking a mode from the out region back to the in region. And this is a very late time mode. So remember, this is future infinity. It's a very late time mode. And when we track it backwards, it's going to skim right by the horizon and be exponentially redshifted. So back to the redshift factor. So this is the key geometry that we need. It comes from the event horizon. That's why we need event horizons for this effect. So this exponential is the key. This is what turns the positive frequency in modes into a mix of positive and negative frequencies in the out basis. So just as a sketch, in the out mode, we have such modes with this u. Remember, u is the time measured far away. And if we rewrite it using the capital U, then using this relation, then we're going to get this thing over here, which is not a single frequency in U. It's a superposition of positive and negative frequencies. And it turns out that this capital U, this local time near the horizon, lines up with the usual advance time in the distant past for rays that just skim the horizon as the rays that we're looking at. So this is how the collapse maps early modes to late modes with an exponential delay. And this distortion, this is actually a distortion in the vacuum. The vacuum gets distorted because positive frequencies are mixed with negative frequencies. This yields a steady particle flux at infinity. So what did Hawking do? Hawking modeled gravitational collapse. He quantized the field on that background. He tracked modes from the far future to the far past, as we did, just skimming by the horizon. Then he computed these Bogoliubov transformations, which is just a fancy way to say a change of basis transformation relating the in and out bases. And he found that the vacuum of the distant past, that includes no particles, contains particles at the distant future. And from these Bogoliubov coefficients, you can get an occupation number. And this might look familiar. This is just a Planck distribution with some temperature. So this is a Planck distribution with a temperature that is non-zero. It has to do with the mass of the black hole. And this is a celebrated result that black holes radiate. So that was the quickest route to Hawking radiation. Are you with me? It's okay? Okay. Now, what reaches infinity? So I just kind of said that it's thermal radiation, but what reaches infinity is a bit different. So on the way out, so these waves, that you see them close to the horizon, these waves scatter out to infinity. So they scatter off the curvature and angular momentum barrier in the following way. So this is some barrier that exists outside the black hole. The event horizon is here, infinity is here. You have an incident wave. It has a transmitted part and a reflected part. So some of it is reflected back into the black hole, but some of it is transmitted to infinity. So we have a transmission probability. This is called the gray body factor, this gamma. And the flux that we find at infinity is this gray body factor times the thermal radiation. So the radiation is in a way filtered by the curvature. So it's not black body radiation, it's gray body radiation. Okay, some numbers, because this is an astrophysics colloquium. Some numbers. So I'm going to put back all the constants that I set to 1. H bar and C and G Newton are back. And this is the temperature. So the temperature goes like 1 over the mass. And if we write it in solar masses, this is what we get. Very, very small. So it's very tiny for a solar mass black hole. So for example, let's say we have a black hole of 10 solar masses. The Hawking temperature is merely 6 nanokelvin. Just for comparison, the cosmic microwave background is 2.7 Kelvin, much, much larger. So this is actually totally undetectable. But if you have a very small black hole, say the size of an asteroid, say 10 to the 15 grams, it corresponds to a Hawking temperature much larger. It goes like 1 over the mass. So this is in the gamma ray regime. Another quantity we can look at is the rate of energy loss. So I guess you all know the Stefan Boltzmann law, that the luminosity goes like the area times the temperature fourth. So let's plug in the temperature, the Hawking temperature, and we get this number. So we get 10 to the minus 55 solar luminosities. Yes, it's funny. Times solar mass over the mass squared. So the bigger the mass, this is even smaller. But the smaller the mass, this can be big, if you are talking about very small black holes. Okay. Another number we can look at is the evaporation lifetime. We can find it from the luminosity, because the luminosity is the rate of mass loss. So the evaporation time scale goes like that, like the mass to the cubed. But it's 10 to the 67 years. How old is the universe? 10 to the 10 years. Okay, so this is completely irrelevant astrophysically. So for example, for a 10 solar mass black hole, the evaporation time scale is 10 to the 70 years. Yeah, but if you look at a small black hole, which has the mass of a small asteroid, then the evaporation time scale is like the age of the universe. So these black holes were supposed to be evaporated by now. Now, astrophysical implications. So I hope you have seen that for stellar mass black holes, which we know exist, the effect is extremely negligible. But for primordial black holes, which we don't know exist, the smaller the mass, the higher the temperature. So they have shorter lifetimes, potentially within the age of the universe. and they have potentially observable high-energy photons, but so far we haven't detected them. So far we haven't detected Hawking radiation. Hawking radiation is still a theoretical result, not detected. And these non-detections constrain the abundance of these primordial black holes, despite there are many theories that use these primordial black holes to explain dark matter and all kinds of things. So far we haven't detected them. Okay, so these were some numbers. Now, some FNQs. If nothing can escape a black hole, how can it radiate? So nothing escapes from the inside of the horizon, but the Hawking radiation is generated by quantum effects outside the horizon. So, and this energy ultimately comes at the expense of the black hole mass. What are the particles that make up the Hawking radiation? So a rule of thumb is that a species appears once the temperature surpasses its rest mass. So for large black holes, effectively only massless particles, so that's why people focus more on massless fields like photons and gravitons. But at the late stages, when the temperature rises, it can be also the other massive particles. Now, some of you might have heard about the popular pair production picture of particles being created, like pairs of virtual particles being created very close to the horizon, and one falls and one escapes, reducing the black hole mass. But I would suggest taking this picture as a mere intuition. But the actual derivation, you now all know it. It's the mode mixing and the mapping between vacuum states. That's the actual derivation, and it doesn't have to do with pairs of particles. Okay, that was the introductory part. Good. So now for my work, and the title of this is No Fireworks. By the way, the title of the paper is much more technical. It's not that. Okay. So as we've seen, when a compact object collapses to form a black hole, quantum field theory predicts the emission of massless particles, which carry energy to infinity. And this emission process relaxes to a steady state known as Hawking radiation. So this is the Hawking radiation. I denote it in this way. But the question is, where in space-time does this Hawking radiation energy come from? Or in the words of Chen, Unruh, and collaborators from quite recently, the origin of the energy in black hole evaporation has been a long-standing issue, which is still not entirely settled. So clearly, the Hawking radiation energy comes from the strong field region. When I say strong field, I mean when we are a few masses away from the event horizon, not too far away. But exactly from what part? So now there are two options. And I will start with option 2 written here. So if you think about photons appearing here, so you detect photons here, and I ask you where did these photons came from, you might say, well, let's just take a light ray and track it backwards. And if you do that, you reach the surface of the collapsing star. So this is what I wrote here as option 2, is that the energy emerges from the collapsing body itself and propagates in some conserved manner through the surrounding strong field region. And this picture has been out there since the beginning of Hawking radiation. The radiation is produced at the shell, and it persists this day by some researchers. But option number 1 is different, is that the outgoing radiation starts from 0 at this point, when we are extremely close to the event horizon, and gradually develops somewhere in the strong field region over a fairly broad strong field region. So it starts, according to option 2, it starts from non-zero here. According to option 1, it starts at 0 here and develops somewhere here. So here are two coordinates, the u coordinate that we introduced before and the v coordinate, and u goes to infinity at the event horizon. So when u is very large, the surface of the collapsing object has reached its near event horizon value. Okay, and now back to this equation. The only stress energy tensor component we're going to need, and the stress energy tensor was introduced here. The only component we need is the outward energy flux density, which is TUU. So this is the U coordinate. You can think of TUU as rays going in this way, as outward energy flux. Okay? And what reaches infinity is this outward energy flux, this TUU. So the Hawking radiation is this TUU times some area at infinity, so R goes to infinity, so along this line, and at late times when U is very large. So it's at infinity and at late times. This is where the TUU relaxes to Hawking radiation. And again, this Hawking radiation value goes like h bar, which is very small, over the mass of the black hole squared times some gray body factor. Okay, so TUU is the important component we're going to focus on. So if you follow option number 2, in which the energy emerges from the collapsing body and propagates in some conserved manner out to infinity, let's see what happens if you follow this option. So this is the energy outflux. It is, let's assume it is conserved along such a light ray, such a light like geodesic. So if you say this is conserved, then TUU at every point of space-time, at every r, is going to have the following form, according to this option. Now we take it to the surface. So TUU at every point has this form. We take it to the surface of the star, which means just plugging in r equals 2m at late times, because this is the event horizon value. And now in a regular Kruskal coordinate, so this U coordinate, as I said, it diverges at the event horizon, so it doesn't tell us much about the physical content of this statement. To understand what this means physically, we need to go to the time of an observer crossing the event horizon. And this is the capital U, or the Kruskal coordinate, which, as we saw before, is related by exponential time dilation. So if you transform to this coordinate, which is regular at the event horizon, you're going to get the following relation. So TUU in this Kruskal coordinate actually diverges exponentially as U goes to infinity at the event horizon. And that means that we actually have significant back reaction effects. We have something diverging, which might stop the collapse process and prevent the horizon formation. And some people talk about horizon avoidance and stuff like that. Okay, so this is all according to option 2. But in the absence of concrete calculations in 4-dimensional gravitational collapse, it is hard to prove which of the 2 options is the correct one. And the main goal of this work was to present such a concrete analysis. Now I don't have much time, so I will skip a few slides. But what we want to compute is TUU at the surface of a collapsing body. Okay, so it has Schwarzschild outside. We're going to compute TUU at the surface, and we're going to see that it is not the one that we got from option 2. And in fact, it goes to 0 at late times when the horizon forms, in accordance with option 1. So the model we consider is the spherically symmetric collapsing thin light-like shell. So we have a shell of light, and it collapses. There's Schwarzschild outside. There's Minkowski, flat space-time inside. It's a thin shell, okay? And it collapses, and at some point, it crosses the corresponding event horizon, and then a black hole is born, and it keeps collapsing, just like the picture I've shown before. So this is what it looks like on a Penrose diagram. It's a light-like shell. It's made of light, and that's why it looks like that, 45 degrees. So I'm going to skip a little bit. The vacuum state that we take on that space-time is the in-vacuum state, meaning that nothing comes from the distant pass. This is just the in-vacuum state in the Hawking effect. Nothing comes in from the distant past. So that's kind of natural. Now, in flat space-time, this energy this energy flux in the in vacuum, which is the natural vacuum in flat spacetime, it just vanishes everywhere. This is the quantum effect. But by causality, this is also true in our model. So, so we have a flat spacetime inside the shell, and what happens here doesn't affect what happens here. So if we take our observer, when it's in the Minkowski part inside the shell, it is only affected by the Minkowski part. It doesn't know about the shell or about the Schwarzschild that's outside. And this remains the case throughout the interior. So that means that what happens in the interior of the shell doesn't know about the shell, so it's empty. So I hope that I have convinced you that Penrose diagrams make causality so transparent. I just showed it to you. So inside it's 0, but outside it's non-zero due to the space-time curvature. So inside it's 0, and outside it's non-zero. And our goal is to compute TUU, to compute this energy density flux at the outer side of the shell, and then take the shell to the event horizon, let it collapse. So I am not going to show you the derivation because of the lack of time, but so we will jump straight to the result. So what we do, we take this shell, we stop it at a certain point where it has a certain radius, R0, and we compute TUU, the outgoing energy flux emitted from the, existing at the exterior surface of the shell as a function of this radius. So I'm going to skip all of this stuff. I'm skipping. I will say that some really happy cancellations happen. Yes. Another one. So it's actually a very simple computation. Usually these things require a very massive numerical computation, and it's very hard to do renormalization. Renormalization is taking something that diverges naively and extracting the physical quantity. So it's very hard. In this case, it turned out to be very easy because things cancel out. This is all I will tell you. And now the result. So what we found was this outgoing density, outflux density emerging from the shell at the point where the shell is at some radius. So okay, we compute the TUU at this point, and this is what we get. So again, why are we focusing on TUU? This is the component most directly related to the question of the event horizon regularity. As I've shown you, if it's non-zero, we get diverging back reaction effects. But what do we see here? We see this factor. We see R0, so the radius of the shell, minus the Schwarzschild radius of the shell. So as we approach the Schwarzschild radius, the event horizon, this vanishes quadratically in the remaining distance. Okay. Now let's go back, as we did for option 2, to really understand the physical content of this thing on crossing the horizon. Let's go back to the Kruskal-based component, which again, this capital U coordinate is regular on the horizon. And if we do that, so this Kruskal U is related to the small u in the following way, and it vanishes like the distance to the horizon when we are near the horizon. So what happens when we transform from the small u to the large u? We get this factor. Okay, this is just a simple coordinate transformation, but this factor is very important because it's the exact same factor that appears here. So if TUU were not zero, or was approaching zero slowly, then this would diverge when R0 goes to 2m, when we approach the event horizon. But thanks to this quadratic vanishing of the small u quantity, these exactly cancel out, and we remain with a finite TUU in Kruskal coordinates, in the coordinates of an infalling observer. So that's good. So that means that option 2, which was about significant back reaction effects and maybe stopping the collapse process, the black hole the star evaporates even before it has a chance to form a black hole. All these things don't happen. Okay. So what does happen? What we computed was what happens on the exterior surface of the shell as it approaches, so throughout the exterior of the black hole, so throughout. But as it approaches the event horizon value at late times, it vanishes. So let's track the outflux along this late time outgoing light ray. So the geodesic leaves the shell when we are very close to the event horizon, and it propagates to future light-like infinity. And as we saw, the outflux emerging from the shell is negligibly small at this point for such a geodesic. It decays quadratically in the distance to the horizon. So we start at 0 at this point, but we reach the Hawking value at this point in the weak field region. So that means that the evolution, and I can even draw it on the board, so the evolution of the outflux along this light ray, so it starts at 0 quadratically, and it reaches, so what we know is this, and what we know is this. It reaches the Hawking value at infinity. And what happens in between is not so important. These are just details of what happens. It can behave like that. It can grow gradually, monotonically. It can do all kinds of things. But the key point is that. The key point is this quadratic vanishing at the horizon. So that means that option 1 is validated. Again, option 1 is that the outgoing radiation reaching the Hawking value at infinity starts from 0 at extremely small to the event horizon and gradually develops over a fairly strong field region, like I drew here. It develops in some way. But importantly, it starts at 0. So some take-home messages. First, the origin of the radiation. So the energy outflux, which later relaxes to Hawking radiation, starts at 0 at the horizon and gradually evolves outward. No fireworks. So we would have fireworks if we were to assume that that the flux comes from the collapsing body. So no fireworks. We don't have this significant back reaction. So this slow onset, this quadratic vanishing, means that the semi-classical back reaction is still locally negligible and definitely not strong enough to do anything dramatic like halting the collapse. And the big picture is that quantum effects matter, but they don't interfere with black hole formation. They matter, for example, when you accumulate them, when you let them accumulate, they can make your black hole shrink in mass and so on. But this happens along very long timescales. But locally, nothing happens, and black holes can still form quietly, even in the presence of quantum effects. That's all. Thank you.
Thank you very much. As always, we like to give some priority to our students first to ask questions. If you have any questions, go ahead.
So if the flux at the horizon is 0 and then it's increasing outside of that, why, again, if the energy is coming from outside the horizon, does the black hole lose mass?
Okay, so let's draw a picture. So let's draw a Penrose diagram. By now, you are familiar with those. So this is the event horizon over here, and this is the infinity, the future infinity, and the past infinity. Okay, so what we have shown, we were looking at one component of the stress tensor, which is TUU, which is the outgoing energy, which is, we can draw it like that, the energy going along the horizon like that. We have confirmed that this is 0, but we also have another component, TVV. Again, this is the u coordinate, and this is the v coordinate. So TVV is actually in that direction. And we still have non-zero TVV. We have negative TVV at the event horizon. This negative TVV is a negative influx of energy, which causes the black hole to lose mass. But we did not focus on TVV, but rather on TUU, because we wanted to look at these claims of horizon avoidance, for which TUU is the crucial component.
Okay, thank you for clarifying.
More questions?
This isn't a very specific question, but I'm a little confused about what the light shell with the Minkowski spacetime inside and the Schwarzschild outside means, and what it connects to conceptually.
Yeah, so this is the simplest spacetime we could look at. Like physicists do, no friction, everything is spherically symmetric. You know, we make simplifying assumptions, but the underlying conclusions remain. It would be very unlikely that okay, let me draw again this picture. So this is the shell. Okay, this is the shell. There's Minkowski inside, Schwarzschild outside. This is a very simple model, and it allowed us to use causality as well to say that TUU is zero inside. So this helps us to perform the analysis, but of course it doesn't correspond to anything in reality. In reality, we have massive bodies collapsing, so this red line. But it's very unlikely that in the simple case in which the collapsing body is light-like, we reach a certain qualitative result that it wouldn't carry to the more realistic case. So we just showed the argument in the case of, in the simpler case, but it is expected to carry to the more realistic case where this is just the star. Yeah.
Thank you for the very interesting talk. I have so you shared the tragic story of Bob. I have a question about the diagram.
Bob.
Can you actually
Let's go to Bob. Okay.
So you talked about the case where Bob sends messages.
Yes.
I was thinking about the other case. If Ellison actually sends messages periodically.
Oh, Alice sends messages.
Yeah.
Okay.
Then how can I? So what will happen? So
Okay.
at some point, Bob will not get
Yes.
messages because it. Okay.
Yeah. Okay. So this is Alice and Bob. Bob jumps into the black hole, and Alice is outside. If Alice were to send messages to Bob, the inverse thing would happen. Bob would be would receive these very blue-shifted light rays.
Once
So
Bob reaches the singularity, and Ellison actually passes at some point beyond this future light cone passes, then the signal may. So I don't know if I can explain this clearly, but if Bob reaches the singularity there, and if Ellison actually passes this 45-degree line,
Yeah.
then the signal that Ellison sends will not reach Bob. Am I right?
Yes, it will reach Bob. Bob is affected by the outside universe, but it cannot affect the outside universe after it passes the event horizon.
If she waits too long, he's hit the singularity.
Yes, yeah, right. But like if Bob is at this point, and Alice can send a message from this point, and it will reach Bob.
So this is an
Yeah.
analysis like
Yeah.
It